Okay, lecture 5, collision and transition state theories. So you should know those the definitions of these terms. First question, what three things need to happen for a reaction to occur according to collision theory? Well, the first thing is you need a collision. You need the molecules to hit. They need to strike each other. Second, energy, I'm going to really abbreviate this, greater than the activation energy. On the exam, I'm going to say that you need to write everything out. So, well, you're not doing it. Well, if you turned in your exam and then you were to say out your answers to me, that's one thing. And these, it's just easier for me to write large in abbreviated form. So, energy must be greater than the activation energy, and you need the correct orientation. You need these guys to strike. They have to have enough energy. The activation energy is really the energy to break the bonds. So you need energy to break the bonds so that you can reform different bonds. And the correct orientation, you need to have the molecules strike in the right place so that the active sites on each molecule hit each other. So those are the three things that need to occur for a reaction to take place. Draw and label a potential energy diagram for the exothermic reaction. A plus B goes to C plus D. The enthalpy change for the reaction is minus 200 kilojoules per mole. The energy of reactants is 400 kilojoules per mole. The activation energy is 300. Now, when we draw a potential energy diagram, I'm going to try to fit it on screen. Will that fit on? Yeah. So we have energy on this side, and we can say kilojoules, since we're doing kilojoules per mole, put kilojoules per mole. So write it like that. On the bottom, we write progress of the reaction, not time. You can take a reaction and freeze it, and actually freeze it, send it down to a really cold temperature, and stop it in its tracks, and start it, and stop it, and start it, and stop it. So time doesn't necessarily tell you the flow of a reaction, but progress of the reaction does. So that should be on the bottom. You put time, that's wrong. You can certainly put the arrow if you like. And then I used A plus B goes to C plus D because we're going to use a lot of general reactions. If you want me to put in a different reaction each time, it's going to take up a lot of time, especially in the lecture on ground. So you get used to these general reactions. So you can say that A and B, what we do is we put the reactants here, A plus B, and this energy, as stated, is what is it? The energy of the reactants. This is 400. And I use kilojoules per mole here, so we just have to have the number. And then we can make this, so we want to make it something reasonable. So 3, 2, 1, yeah, that'll fit. 5, 6, 7, 8, 9. Just turns out this turn will be 0. That's fine. You don't have to label them all. But what we need then is the activation energy is 300 kilojoules per mole. That's going to be above the reaction energy value. So 400 plus 300, 5, 6, 7. So it should be right here. And so we will go up to there for our activation energy. So this is a potential energy diagram. We're riding up this slope up to the activation energy. And we can even write that here. Probably a good idea to do so. This is EA is equal to plus 300 kilojoules per mole. And then we have this is an exothermic reaction, or the activation, yeah, the energy of reactants. Okay, so the reaction is minus 200. That means it drops below, the products drop 200 kilojoules per mole below the reactants. So down to here. You can just put a dotted line here if you want to indicate. So 1, 2, 3. That should have been straight across. This drops back down to C plus D. And you can say that delta H is minus 200 kilojoules per mole. What we do here is we put A dot 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 B in brackets and put the scroll mark to indicate the activated complex. And that's enough. If you put the scroll mark, you can also point to it as the activated complex. We have EA, we have delta H, we have the concentration, we have the reactants and products, we have the activated complex, we have the axes labeled correctly. Looks like we have everything. That's what you need to do. For exothermic, for endothermic, I'm going to switch over to a different pen so I can just write it smaller, have everything on here. So I like to use the big pen so it's easier to read. But let's do this out. So enthalpy change is plus 300. Activation energy is 2. So make sure that one activation energy actually, so that it will actually, let's see, 200. Yeah, this has to be higher. So we're going to make this. And you can check out 200. You'll see that it just, if I had left that 200, it wouldn't give us a real answer. So that's, I just picked those numbers as I went along. A plus B. Now this is an endothermic reaction, same reaction, but you know I didn't say what A and B are. It could be, they can definitely be different. So again, label this. We have the energy, and we put kilojoules per mole. In the book, well, they use energy per mole. That's fine. They can do that. And then here at the bottom, we'd have progress of the reaction. And then, let's see, so the enthalpy, where the energy of the reactants is, so we'll say this is 0, 1, 2. So this is 200 kilojoules, 2. And we'll put A plus B here. So that tells us what energy we start with the reactants. The activation energy is 500, so that's going to be 3, 4, 5, 6, 7, 8. It's got to be 500 above what we started with, so it would be up here. Just do the best you can to get up to that top of that hill. And then the energy of the reactant, okay, so the enthalpy change is 300, so that's going to be 300 above what we started with. So 1, 2, 3, to go right across there, C plus D. Boop, boop, boop. And then this drops down. So I'm not explaining all the theory that's in the book. It's also going to be on the on-ground lecture. I'm trying to show you how to solve this problem. And a lot of times I'm going to assume that you know certain things rather than go through a 20-minute theory lecture on this and show you how to solve these problems. So if you look in this and say, what is activation energy? What's he talking about here? Read the book, come to the lecture, and it's all in the book, but I'm just showing you how to solve these problems. So the lectures are designed to be that, designed that you know something about the problem coming in, what the equation is that you use, the basic theory. These are how to solve the problems that will be on the exam. So yeah, you don't want the theory lecture in here because it would be, I don't know, instead of this 20 minutes, it would have to be an hour and a half. The book has the material, and the on-ground lecture will have the theory material as well. At the top, you'd put in A is a activated complex. That's the form that it takes. And this is the activation energy from here to here is 500 kilojoules per mole. From here to here is delta H. You went up. Instead of dropping below the reactants, it went up, so this is plus 300. Yeah, and I want to make that clear, so I'm going to say it again and say this is not every aspect of the theory that's not what's covered here. I'm doing sets of problems as supplements to the problems that we do in class and in the book. So you do want to know something about the theory before you come to these calculations. And I think we have the and this would be EA. So we know the activation energy, we know the enthalpy, we have the activated complex. We've labeled the axes correctly with the numbers here. You don't need to have anything, any units here. It's just the progress of reaction. And let me double check. Yeah, in their but in the book they give you the reverse activation energy. I don't worry about that. They show from here to here. That's only if we're doing a reverse reaction. Not worried about that here. So that's as far as I'd want you to go. And that's it.